Hello, Physics 243. In this unit, we will introduce Chapter 12 on sound. Brief introduction to sound. Right off the bat, I want to say something, and that is that studying the perception of sound is different from studying sound as a physical phenomenon. Perception of sound is not the same as the study of the physical phenomenon. So the chapter, since this is physics class, will concentrate on the physical phenomenon, but we will have something to say about perception of sound. There's actually a whole field of physics called psychophysics, which is not quite what it sounds like. Physics for psychos? No. It's the physics of how things are perceived. Okay, so sound, I mean, including colors and things like that. Okay, but what is sound? Well, sound consists of longitudinal pressure waves in the air or in other materials. So sound waves can propagate in water and even in solids. But sound, the way we think about it, is a longitudinal pressure wave in the air. What makes sound? Well, vibrating membranes, strings, columns of air. So vibrating membrane is like a drum, right? The drum head itself is in general terms, a membrane, and you hit it with a stick and it vibrates. And that causes the air nearby to compress, and I'll show you in a second what happens exactly to the air, but that generates sound waves. Or you can pluck a string on a guitar and you see it oscillates back and forth the way we discussed in the previous chapter. Similarly, a piano. A piano is a device where there's a hammer that hits the strings. You can see the strings here, and then they vibrate, creating the sound. That also causes the whole rest of the structure of the piano to vibrate, to amplify that sound. And then columns of air. So like a flute and a clarinet here. The instrument itself encloses a column of air, and it vibrates back and forth. When you blow across the flute, or you blow to make the reed vibrate in the clarinet, you're causing the column of air to vibrate back and forth. And that gives rise to the sound. Okay, so remember the types of waves, right? And they're illustrated here with a sort of stretch slinky toy. Transverse waves look like this, and longitudinal waves look like this. So the lower one here, the longitudinal waves, this is what sound waves are like, as you'll see in a moment. In air, in fluids, you can't get transverse waves, because notice that for the slinky, this part of the slinky is going to get pulled down by the rest of the slinky, and this part of the slinky is going to get pulled up by the rest of the slinky. But that doesn't happen in a fluid, right? In a fluid, if you move your hand this way, what happens is you make a longitudinal wave going up. Okay, so notice in the longitudinal wave, you've got regions where the slinky is compressed, the coils are closer together, and regions where they're stretched out, right? Stretch, compress, etc. So here's a picture of sort of a sideways picture, which is strange, of a drum. Maybe you can think of it as a speaker. And this is the membrane of the drum head, or the speaker, what do you call it? The membrane of the speaker, whatever. Anyway, that vibrates back and forth really quickly. And this is the air above it, or to the side of it. And the motion of that membrane compresses the air here locally. And then this region of compressed air then moves outward. And by that time, the membrane has gone the other way. And that causes the air in that region to be rarefied, to be made less dense. The pressure lowered, there's an expansion there. And then that repeats. So you see that here's a region of compressed air, which has already come out and propagated all the way to here. Here's another one that propagated even earlier. All right, so another way to depict this is to do it like this. So here's a representation of what we just talked about, the air. And here's a graph of the density of the air versus space. Right, now this is a snapshot. Right, this is what the air looks like at one moment in time. And so you see that the density is low here, and then it's higher here, and then lower and higher and lower. Okay? And then in time, what happens is this waveform that you see down here, and these regions of compressed and rarefied air, well, they move to the, let's say, to the right. So imagine this whole thing moving to the right. So I found this cool animation. Check this out. It's by Dan Russell from Penn State. This is a tube. You can imagine a tube of air. And on one end is some surface which vibrates. So I wrote here the surface of a speaker. See how it's moving back and forth? Could be the surface of a membrane. And everything is much slower than it would be in real life. Like in real life, this would go back and forth several hundred times per second. But slowed down like this, you can see how the surface here is pushing together the molecules and then sort of drawing them apart and pushing them together and drawing them apart. And these regions of compressed molecules propagate forward. There they go. They march along like that. Now he's also colored a couple of the molecules. Here's a red one. There's another red one. There's another red one. And notice their motion. Here's the same data with little arrows to make you pay attention to this. The motion of the molecule is just back and forth. Just like the motion of the slinky, the chunk of the slinky is just back and forth. Similarly over here and over here. So he's got an arrow to indicate the motion of the particle, but he's also got an arrow to indicate the wave. So you see there's the propagation of the denser part of the wave, and it moves right along. Okay, so that's what sound is. And again, this happens much, much, much faster than what you see here. This is a very much slowed down view. Now it's a wave, so it has all the characteristics that we've already talked about. So this, for example, could be what I showed you before, the graph of the density of the air versus space. So it's dense air and then rarefied air, dense air, etc. And so there's an amplitude. The amplitude would be in density. There's a wavelength in space. And since this whole thing moves to one side, let's say to the right, the region of higher density then shifts over to the right. It moves along. So there's a frequency and there's a period, certain number of cycles per second, and the amount of time it takes for one of these waves to pass a place in time. And as it moves, there's a wave velocity. Remember this relationship, that the speed of the wave equals the wavelength times the frequency. That's an important thing to remember. Also, sound, of course, travels in 3 dimensions. So what I showed you before was essentially just one dimension in a column of air, but it actually happens in 3 dimensions. So here you see this a source, wherever it is, and outward are the waves, where let's say that the darker blue is the regions of increased density of air, and then the white one is where the density is less. And so these things propagate outward in space in all directions. All right, a couple words about the speed of sound. So speed of sound is different in different materials. So there's a table in the book, page 329, and it shows you the speed in meters per second for various things, or air, helium, different in water. There it is in water, and seawater it's a little bit different. And even in metals, so iron and steel, glass, aluminum. So you can have sound in an iron bar. How do you make it happen? Well, you hit it with a hammer. And those sound waves go very, very fast, because they're restoring, the effective springs between the molecules of the iron are very, very stiff. Much stiffer than between, say, the molecules in the air, where they have to sort of bump against each other and push against each other apart. Now, the speed of sound also depends on temperature, especially for gases. So in the entry here, notice in the list here, it says that these various speeds are listed for 20 degrees Celsius and at a pressure of 1 atmosphere, except for this one, where it says air at 0 degrees and presumably 1 atmosphere. And it's different, right? At 0 degrees, it's a little bit slower. There's a empirical relationship like this, which is given in the book. So the speed is 331 plus 0.6 times the temperature, where temperature is given in Celsius. And that gives you a result in meters per second. So for example, you plug in 0 degrees, you can get the 331 that's listed here. And if you plug in 20 degrees Celsius, which is about 68 degrees Fahrenheit, plug it into here and you'll get the entry here, 343. meters per second. By the way, that's about 767 miles per hour. So sound is quite fast, but it is glacially slow compared to the speed of light, right, which is 186,282 miles per second. So you see the flash of lightning well before you hear the thunder. Okay, so this is important to know that speed of sound, especially in gases, has some temperature dependence. All right, so that's it for a quick introduction to sound. Next up, we'll talk about the perception of sound a little bit and decibels. So I'm sure you've heard of decibels. We'll tell you what decibels really are. Okay, see you in the next one.